Imagine a white-hot cylinder of cast iron, freshly pulled from the furnace at a forge in Shropshire. It weighs over 1,000 pounds. Its rough exterior still glows with the memory of molten metal, and it sits waiting for a machine that did not exist just 1 year ago. A boring mill so precise, it will carve the interior of this cylinder to a tolerance no human hand could ever achieve. This single iron cylinder, once bored to perfection, will become the beating heart of a machine that changes everything. A Boulton and Watt steam engine. And the story of how it gets from this raw, glowing lump of iron to a working engine that can drain a flooded mine or blow air through a blast furnace is one of the most extraordinary manufacturing journeys of the 18th century. To understand how we arrived at this moment, we need to go back a decade to a workshop inside the University of Glasgow. It is 1763, and a young Scottish instrument maker named James Watt has just been handed a small model of a Newcomen engine, sent to him for repair. The boiler is no bigger than a common tea kettle. The cylinder is only 2 inches across and 6 inches in stroke. Watt looks at it and calls it a fine plaything. But the moment he sets it to work, he notices something deeply wrong. The boiler, though it seems large enough, cannot produce steam fast enough. After only a few strokes of the piston, the little engine sputters and dies. Watt stokes the fire. He blows harder. More steam rises, but the engine still refuses to work properly. Where a lesser mind might have walked away, Watt becomes utterly consumed. He goes to his books. He constructs a special boiler to measure precisely how much water evaporates in a given time and how much steam every single stroke of the engine devours. And then he stumbles upon a fact that astonishes him. Steam, when it condenses, heats 6 times its own weight in cold water, down to 212 degrees. He does not understand why. He mentions this to his friend Dr. Joseph Black, who explains to him the theory of latent heat.
Now,
it is this discovery, this invisible reservoir of energy locked inside steam, that sets Watt's mind on fire. The problem he now realizes is devastatingly simple. In a Newcomen engine, cold water is sprayed directly into the cylinder to condense the steam and create a vacuum. But every time that cold water enters, it chills the cylinder walls. And every time the next blast of steam comes in, nearly 4/5 of it is wasted, simply reheating those cold iron walls before any useful work can be done. The engine is destroying most of its own power. Watt writes that to build a perfect steam engine, the cylinder must always be kept as hot as the steam entering it. But to create the vacuum that drives the piston, the steam must also be cooled below 100 degrees. These two requirements seem completely impossible to satisfy at the same time. For 2 years he gropes in the dark. He tries one expedient after another. He later says he was misled by many an ignis fatuus, many a false light. Then, one Sunday afternoon in the spring of 1765, he goes for a walk on Glasgow Green, a quiet meadow used for bleaching and grazing. His mind, as always, is running on steam. He passes the old washing house. He walks as far as the herd's house. And then suddenly, the idea strikes him. Steam is an elastic body. It will rush into a vacuum. If he connects the cylinder to a separate sealed vessel, kept constantly cold, the steam will rush out of the cylinder and condense there, without ever cooling the cylinder itself. He does not even need to finish his walk. By the time he reaches the golf house, the entire invention is arranged in his mind. The separate condenser, the air pump to remove condensed water, the sealed cylinder top, the steam jacket to keep everything hot. On the very next morning, he is up at dawn, borrowing a large brass syringe from a college friend, the kind anatomists use to inject wax into arteries, and he begins building his first model. It works. The piston lifts 18 pounds, as quick as the blow of a hammer. But between a brilliant idea working in miniature and a full-scale engine that can power industry, there lies an enormous gulf. And that gulf is made of iron. Watt needs cylinders, large, accurately bored cylinders, and the collective mechanical skill of Glasgow cannot provide them. The cylinders available are not bored at all. They are hammered into shape by hand, and they are hopelessly out of round. Steam leaks past the piston in every direction. Watt writes despairingly that his greatest obstacle is always the smithwork. His leading mechanic, whom he calls "my old white iron man," dies. A beam breaks on his prototype. He is running out of money. For years, the engine devours his savings while producing nothing in return. He takes up land, surveying just to feed his family. Enter Matthew Boulton. By the early 1770s, Boulton is already one of the most remarkable industrialists in England. In 1761, he built the Soho Manufactory on a barren hilltop 2 miles north of Birmingham, a place so bleak that people thought he was mad to put a factory there. But within a few years, he has turned it into the largest hardware manufactory in the world, employing between 600 and 700 workers, producing metal buttons, buckles, watch chains, silverware, and ornamental goods that are shipped to every corner of the globe. The Soho Manufactory is powered by a watermill on the tiny Hockley Brook, and this is Boulton's chronic headache. Floods in autumn, drought in summer, ice in winter, any of which can shut down production entirely. Boulton does not merely want a steam engine, he needs one. In 1774, Boulton persuades Watt to leave Scotland and come to Soho. Watt ships his prototype engine down from Kinneil in pieces. The Soho staff reassemble it and get it working better than it ever performed in Scotland. But even these skilled Birmingham craftsmen cannot hammer the cylinder accurately enough to prevent steam from escaping around the piston. It seems the invention might be doomed by the very limitations of the age that produced it. And this is where a man known to everyone in the iron trade as Iron Mad Wilkinson enters the story. John Wilkinson is an ironmaster obsessed with his material. He eats off iron plates. He will eventually be buried in an iron coffin. In 1774, the same year Watt arrives at Soho, Wilkinson patents a device that will change manufacturing forever. It is a new method of boring cannon from a single solid casting, and its secret lies in one crucial innovation. The boring bar, the shaft that holds the cutting tool, passes entirely through the cylinder and is supported at both ends. Every boring machine before this used a cantilevered bar, supported on only one side, which meant the cutting tool would wander and wobble as it advanced, producing a hole that was never truly round. Wilkinson's machine holds the bar rigid from end to end. The cylinder rotates around the fixed bar. The cutting tool advances steadily, shaving away iron in perfect circles. For the first time in history, a large hollow cylinder can be bored to a degree of precision previously unimaginable. Boulton knows of Wilkinson's technique. He understands immediately that what can bore a cannon can bore a steam engine cylinder. He connects Wilkinson with Watt, and the ironmaster sets to work at his boring mill in Birmingham, deep in the Welsh borderlands. The process is extraordinary to witness. A massive casting of iron arrives from the blast furnace, rough and pitted on the outside, its interior a crude hole left by the core during casting. It is mounted in Wilkinson's machine, chained and bolted to the rotating mechanism. The boring bar is threaded through, its cutting head positioned at the entry. When the mill is set in motion, powered by a water wheel turning with relentless force, the cylinder begins to rotate slowly around the bar. The cutting tool bites into the iron, and fine shavings of metal curl away like dark ribbons. The sound is a deep grinding roar that fills the entire works. Water is poured over the cutting surface to cool it and wash away the cuttings. Hour after hour, the tool advances, fraction by fraction, carving the interior into a smooth, true circle. When it is finished, the bore is so accurate that the gap between piston and cylinder wall is reduced to a thickness barely perceptible. This is the breakthrough Watt has waited a decade to achieve. With Wilkinson's cylinders, the Boulton and Watt engine finally becomes a practical commercial machine.
Indeed.
In 1775, the partnership between Boulton and Watt is formally established. Parliament extends Watt's patent until 1800, giving them a quarter-century monopoly on the separate condenser engine. The business model they adopt is unlike anything the world has seen. They do not at first build complete engines at Soho. Instead, Boulton and Watt design the engine, prepare detailed drawings and specifications, and then contract the manufacture of individual components to specialist makers across the country. The cylinders go to Wilkinson. Beam castings, pipes, and valve parts are sourced from various iron founders. At Soho itself, Boulton's skilled workforce produces the smaller precision components: the valves, the regulating mechanisms, the brass fittings, the connecting rods, and the intricate parts of the separate condenser. The Soho Manufactory itself is a revelation. Visitors who come expecting a grimy forge are stunned to find a complex that looks more like a Palladian country house than a factory. The principal building, constructed between 1765 and 1767, has a grand symmetrical facade. Behind it, arranged around courtyards, are the specialized workshops, rolling mills, stamping rooms, plating shops, and fitting rooms, each dedicated to a specific stage of production. In front of the building, a large pool feeds water to a great water wheel that powers the rolling and stamping machinery. The courtyard displays an impressive number of tools and mechanical inventions that contemporary visitors describe as superior in variety and simplicity to anything else in the world. The workers here are not unskilled laborers. They are trained craftsmen, fitters, turners, smiths, and assemblers, many of whom Boulton has personally recruited and developed. When the components for a new engine arrive at Soho from Wilkinson and other suppliers, the assembly process begins. Watt himself often supervises the critical stages. The separate condenser, the invention that makes everything possible, is a vessel of copper or tinned iron, fitted with pipes through which steam from the cylinder rushes to be condensed by cold water surrounding it. An air pump, driven by the engine itself, continuously removes the condensed water and any air that leaks in, maintaining the vacuum that gives the engine its power. The cylinder, bored by Wilkinson, is mounted vertically and enclosed within an outer jacket through which steam circulates, keeping the working cylinder constantly at the temperature of live steam. The piston, sealed with grease and oil, rather than the water used in Newcomen engines, slides smoothly inside, its fit now so precise that barely a whisper of steam escapes past it. The first truly successful Boulton and Watt commercial engine is completed and installed at John Wilkinson's own ironworks in 1776, a fitting destination, since it is Wilkinson's boring mill that made the engine possible in the first place. The engine has a cylinder 50 inches in diameter, an enormous piece of engineering for its time. When it fires for the first time, consuming only a fraction of the coal that a Newcomen engine would require, the result is unmistakable, a machine of startling power and remarkable efficiency. The Boulton and Watt engine uses only 20 to 25% of the coal consumed by a Newcomen engine of comparable power. Word spreads quickly through the mining districts of Cornwall and the coal fields of the Midlands. Mine owners, desperate for more powerful and economical pumping engines, begin placing orders. Each engine is essentially a bespoke project. Watt and his draftsmen prepare individual designs tailored to the specific requirements of each installation: the depth of the mine shaft, the volume of water to be pumped, the available fuel supply. Detailed drawings are sent to Wilkinson for the cylinder, to other founders for the beam and structural castings, and to the Soho workshops for the precision components. Watt dispatches his most trusted men to supervise the erection of each engine on site. One of the most capable of these erecting engineers is a young Scotsman named William Murdoch, who will later become famous in his own right for inventing gaslighting. The production numbers tell the story of a revolution in motion. Between 1775 and 1800, the partnership produces 496 engines. Each one is assembled from components sourced from multiple locations, brought together by the organizing genius of Boulton and the engineering precision of Watt. The financial model is equally innovative. Rather than selling engines outright, Boulton and Watt charge customers a royalty based on the fuel savings their engine achieves compared to a Newcomen engine. They are literally selling efficiency itself. By the early 1780s, Watt has improved his design further. He develops a double-acting engine in which steam drives the piston in both directions, effectively doubling the power output from the same cylinder. He introduces the sun and planet gear, a mechanism that converts the reciprocating motion of the piston into rotary motion, allowing the engine to drive mills, looms, and factory machinery, not just pumps. This transforms the steam engine from a specialist mining tool into a universal power source for manufacturing. Back at the Soho Manufactory, Boulton is among the first to apply this new rotary engine to his own production. The old water wheel, so long at the mercy of the seasons, is supplemented and eventually surpassed by steam. The factory that helped birth the steam engine now runs on its own creation. Boulton even adapts the technology to power a revolutionary coining press at the Soho Mint, established in 1788, producing coins of a quality and consistency never before seen. The first steam-powered mint in the world. But in the mid-1790s, a crisis threatens the entire enterprise. The Wilkinson brothers, John and his brother William, who have been the exclusive suppliers of Boulton and Watt cylinders for nearly 2 decades, fall into a bitter quarrel and cease production. With Watt's patent due to expire in 1800 and competitors poised to flood the market, Boulton and Watt have no choice but to take the momentous step of bringing all engine manufacturing under their own roof. In 1795, they established the Soho Foundry at Smethwick, a canal-side site purpose-built from the ground up for the complete manufacture of steam engines. It is the first factory in the world designed specifically and solely for this purpose. The Soho Foundry is organized with a sophistication that anticipates modern manufacturing by more than a century. Production is divided into 3 main departments: the foundry department, which casts the iron parts, the smithy department, which forges the wrought iron components, and the fitting department, which machines the parts to precision and assembles them into finished engines. Each department operates as a separate accounting center. The workshops are arranged spatially along the flow of production, so that materials move logically from one stage to the next, minimizing wasted time and effort. Products are built from standardized, interchangeable parts. Work is broken down into small, specialized tasks. One surviving document from 1801 describes how a team of 4 specific workers is to be constantly employed in fitting nozzles, and nothing else. William Murdoch, recalled from Cornwall, solves the problem of excessive vibration in the boring mill machinery by introducing small dedicated beamless engines, each powering a single boring machine. And in December of 1798, Murdoch installs a small gas retort in his laboratory at the foundry, connecting it by a tube of about 30 or 40 feet to the main building, making the Soho Foundry the first industrial building in the world to be lit by gas. Workers who once labored by the dim flicker of tallow candles now work under the steady glow of gaslight, extending the productive hours deep into the English winter darkness. What began with a young Scotsman puzzling over a broken toy engine in a university workshop has become, in the span of a single generation, The foundation of the modern industrial world. From James Watt's Sunday afternoon revelation on Glasgow Green, through years of frustration with hammered cylinders that leaked, and mechanics who could not execute his vision, through the precision of iron-mad Wilkinson's boring mill, through the commercial brilliance of Matthew Boulton, and the organizational genius of the Soho works, every step in this chain was essential. Remove any one link, and the engine does not work, the factory does not run, the revolution does not happen. But here, in the smoke and thunder of the Soho foundry, with its boring mills screaming against iron, and its fitting shops alive with the tap of hammers and the hiss of steam, a new age is being forged, not from theory or philosophy, but from cast iron, sweat, and an absolute refusal to accept that a cylinder cannot be made round enough.